Okay, so to review what we've talked about so far, so if you looked at the simulation, hopefully, if you haven't, go back and do that. And you can see that the first thing that needs to happen for a reaction to occur is we need to have a collision, so reactants need to collide. Now this assumes that we have two reactants, and there's a lot of reactions that just have decay or some type of decomposition where just a molecule breaks apart by itself, but we're looking specifically at a collision, which is a little bit more common. So one, reactions have to collide, so higher concentrations can increase this rate of the collisions, lower concentrations can decrease it. So once that happens, when a molecule collides, they have to have enough kinetic energy. So you need to have the required. We'll do it this way. So reactants that collide, so meet requirement 1, must have the required kinetic energy. I'll just rewrite this. Kinetic energy, or Ke, and that is the sum of the energy difference between the reactants and products plus the activation energy. Now, this term right here is only important if the reactants have a lower energy than the products. In the case where the products have the lower energy, then this term is not involved with the Ke. It's just the activation energy, and we saw that in the graphs. So what other components? So you have to have collide, you have to have enough kinetic energy, but there's a couple other stipulations. And then the next one is orientation. So molecules, we draw them as spheres. So we actually, I'll write it out first. So molecules need to have the correct orientation when they collide. And so the reason is, we have molecules. So we always kind of draw molecules as being these circles. So we say like A and B, and we're drawing a collision. But it might turn out that A actually looks like this. Again, we're still using kind of a cartoon characterization, but it works very similar. And B looks like this. There's only one way in which they will fit together. And so the higher the specificity for this collision orientation, the less likely reaction will occur. And so there are a couple ways that we can increase this. One is that we have an enzyme acting as a mediator to kind of orientate molecules in a specific way. So enzymes can do that. Or they just reactions that have this high orientation specificity just go really slowly. Because not only do you have to meet the first two requirements, collision and energy, you also have to meet, are you in the right orientation? So it's kind of a numbers game. And you can always increase these numbers with temperature or with enzymes. Enzymes can do a couple things. So we'll talk about that next. So again, orientation is important. And then we already talked about activation energy. But an enzyme is called a catalyst, or we can classify it as a catalyst. A catalyst, which is a lot of times an enzyme. Not always. Enzymes are what we find a lot in our body. We talk about that do things for chemical reactions. So like, for example, we talked about lactase is an enzyme that helps break down lactose. So it allows for our body to break down lactose molecules. And so, and most of these kind of dietary defects and a lot of genetic defects we find in general are a lack of a gene encoding for an enzyme that allows a chemical reaction to occur. And if you don't have a chemical reaction to occur, it can have a phenotype or have different diseases basically come out from that. Not all, but a lot are in this way, especially genetic diseases that account for not having a missing gene or having duplicates, mainly missing. So a catalyst, an enzyme, can lower the energy barrier which would be the activation energy, or by decreasing the activation energy. You can't change the energy of reactants product, so it's just the activation energy, and increase the rate, or increase the rate of the reaction. Okay, so we're going to lower the energy barrier. And so it lowers it both ways, so it doesn't actually, it'll make a reaction happen faster on a faster time scale. It doesn't actually change how much A and B you have. And you can see that in the simulation that the removing the barrier makes it easier to go from reactants to products and products to reactants. And you can check that out and see. So, but it might take a reaction that would have taken days to happen. It might take minutes, and so that's actually really important. And that's a lot of times how our body will manage these very complex reactions. Where if I need an upregulation, so like let's say I just ate a bunch of bread, I need to break that down, and so I need some insulin released. We will have enzymes that will do that, and they should work they normally work very slowly, but maybe we add a catalyst into our reaction mix, and then that's going to make the reaction happen much faster. So enzymes are a nice way to modulate time frames for chemical reactions that we want to happen slowly most of the time, but quickly at other times. So it's pretty cool. So enzymes are very important for making chemical reactions happen quickly that normally wouldn't, by decreasing the activation energy. So if we look at graphically what that looks like, so this is still energy. We have we'll do the one where we have the reactants lower energy than the products, P. And this is the normal uncatalyzed hump. So this would be the activation energy that we would find for an uncatalyzed reaction. And then if we have add a catalyst, so this is blue is add a catalyst, which would be like adding an enzyme. Okay, we can use these terms interchangeably. Then we'll see that we don't change the reaction or product energy level, but we can make that hump much smaller. And so this right here, EA catalyst, so this is the new activation energy with a catalyst. Okay, so it's activation energy, and then the CAT, comma CAT is how we abbreviate that, where the activation energy that has a catalyst is less than the activation energy without. So that's a key point. So that's just graphically showing you what we have already talked about and what a catalyst does. So those are the three main ways in which we can modulate. So we can also the orientation we can't change. Catalyst can kind of help with that, but it's still like adding a catalyst will do a couple things. So changing the concentration. So just to summarize, so if I want to make a reaction, so if I want a really fast reaction, I want a fast reaction. So I want it to happen, and I want it to go fast. Then the things you want high concentrations. Okay, you want high temperature that the reaction's occurring at. You want to add a catalyst or an enzyme. Okay. Now the thing that again, orientation also makes a difference, but that's not something that you can change. Just like you can't change the energy of reactants and products. So those are the if you want a fast reaction, if you want a slow reaction, if you don't want a reaction to happen at all, or you want it to happen really slowly, then you're going to have the opposite of all these. This is one. You want to have low concentration. You want to have a low temperature. And you want to have no catalyst. Okay, so that's, again, reactions occur not by some magic. It happens because things collide and they have the required energy orientation to cause a reaction to occur. And so we can summarize kind of the two main points of the reactions occur. We've talked about one of them already in this discussion. So, and this is kind of a big take-home for the not just this class, but all chemistry classes. Why do things happen? Chemistry is measuring what and the why and the when and the how things happen. And so this is basically the best way to predict if a chemical reaction will occur. So there are the two main driving forces. For reactions that occur spontaneously. So this means no additional input of energy. There are the two main driving forces. So driving forces, the first is what we've talked about, that we have higher energy reactants. These are going to be less stable. Are converted to lower energy products, which are more stable. And I'm going to draw a picture of that. So if we remember, that's a situation that we saw high energy reactants being converted to low energy products. So okay. So that's a summary of what and the why we kind of talked about, looking at the different ways, different factors, and how this makes a big difference. And so if we have a reaction that goes from high energy reactants to low energy products, that's more likely to occur. But it's not always. So just because you have it doesn't mean that your reaction will occur. The second one is something that we won't actually talk about, but is really important in understanding why things happen. And it has to do with something called entropy and order. It turns out that order is bad. Order is something that we have to continually try to fight. That high order systems are not preferred, and that they will go to disorder as quickly as possible. And a good example of high order system might be your sock drawer. That you at some point you decide, I'm going to find or pair up every one of my socks and throw out any ones I can't find. And so at that point, you have the highest order of your sock drawer possible. All your socks are washed and they're all paired correctly. Over time, your socks get lost, they get mismatched, they're not in the sock drawer, and you might put them back. And so to keep your sock drawer in this high order state in which you have all of them clean and matched takes a lot of energy. And if you stop doing that, stop inputting the energy, your sock drawer will go into chaos or disorder. And that's basically true for all chemical reactions, that you have to continue to input energy to keep a system in high order. And systems will spontaneously go from high order to low order. And that's why we will preferentially favor reactions that do just that. So that is to say that chemical reactions where the order of the products is less than the order of reactants. So this is going from reactants that are high order to products which are low order. This is favorable. So that is to say that if you meet both requirements, if your reactants are high energy and they are also high order, these are not always related, but they can be, then your products are low energy and low order, then you are almost guaranteed to be a spontaneous reaction at all temperatures. If you meet one of the requirements, let's say you have high energy reactants going to low energy products, but you're going from low order to high order, you may or may not be spontaneous. It might be temperature dependent. Okay, and there's a whole class of thermodynamics when we talk about this. So we were just really summarizing, but I want you to know, in general, temperature and energy of reactants and products play a huge role in predicting if a reaction will happen, but it's not the only thing. There's something else that has to do with order, which makes a big difference. The actual term we use, just so you see it, looks like energy, but it's called entropy. And so entropy is a measure of order, or sorry, disorder. So this is disorder. So if you have a high entropy system, it means you're very disordered. If you have a low entropy system, it means you're very ordered. We want to favor the highest entropy system possible, or lowest order. Those tend to be the most stable. So going to a low energy products is not the only requirement. It does help. And if you also go from a high order to low order product, and how order is measured in products and reactions, don't worry about, or systems, but just know that that also factors into reactions that are spontaneous. It also means that we can have chemical reactions that do not meet this. So we can actually have a chemical reaction that goes in this direction. And even though we know we have reactants that are products. So even though we have this difference that doesn't meet the first requirement, it can still be spontaneous if the second requirement is met and you have high order reactants going to low order products. So it's not as simple as just energy reaction products. There's a little bit more to it. I just want to acknowledge that exists, but we're not going to really go into it that much. But these 2 points are really important to know in terms of predicting if a reaction will happen. And if you meet both of them, you will always be spontaneous at all temperatures. And that's a pretty cool thing to be able to predict if you know these 2 things. So that is it for why chemical reactions occur.